So this video has two parts. Both of them will cover question 13 because question 13 is quite a long question, so I decided to break it into two videos. Okay, so there will be 13 part A, and then there's 13 part, I don't know, B, C, D, up to you. Later we will decide. So usually the first question in your section B is what we call a database question. They will give you a bunch of data and you need to make sense out of it. So let's recall what the question is on. So basically they are telling you that there's a fire alarm system, there's a bell. The bell has such rating. What does this rating mean? This rating means that this bell, if you provide 9 volt, it will give you an output of 120W. Okay, and then it gives you this table, and this table are telling you that this is what the wire can support. So if you select this diameter, this wire can support up to a power of 20. So for example, if you use a certain type of wire, you connect to a certain appliances. If this appliances is 20W, then okay, you should choose a wire diameter that is of 0.20 mm. Okay, so this is what the table is about. And then they say that for this table, I try to, when I set this question, I try to be a little bit tricky. I say that this table, right, works on a 5 volt supply. So all this thing, right, is based on 5 volt supply. Okay. So now in part I kind of is asking you that, okay, now I have this bell. Can you select diameter for me if I go and connect it to a 5 volt supply? So basically I'm asking you, right, you need to do two things. Number one is you need to figure out if now for this bell, my input changed to 5 volt, what would be my output power? And from this particular output power, let's call it XXX, you need to look at the table over here because this table works based on 5 volt, so you can use that. You need to look at your XXX and then you compare with all this power and you select a diameter accordingly. So you need to do kind of like 3 processes. So at first I thought that this would be rather easy because we have actually done this in your homework on practical electricity. This is especially true when you need to figure this out. So I got a shock when I see responses that were completely wrong, and the mistakes is and that we have covered the mistake in our lessons. So let's take a look at this. The first kind of misconception that always happen is that student will tend to think that, oh, if I change 9 volt to 5 volt, I multiply 9 by 5 over 9, and therefore I should multiply the same fraction to the power. This is wrong. You can't do that because power and voltage is related by P equals to V square over R. There's a square there, so you can't do that. Yeah. So what you need to do is you need to find out the resistance first, because the resistance of the bell, okay, the R over here, right, will be fixed. By changing the input voltage, right, your resistance is fixed. But I am still having a lot of you who like to use P equals to VI. When you use P equals to VI, okay, fine, you can use it, no issue. You can find the current over here, which is this. But this current, right, is for the input V equals to 9V. When you change your input to 5V, because you have a lower EMF, you are going to get a smaller I. And so you cannot do something like that. So what I mean is, some of you do this, and then they say that, oh, okay, I want to find power, right? So I want to find this new power when I put a new voltage 5 here. You cannot just substitute this. This is wrong because this current is for an input of 9 volt. So they are different. You can't do that. Okay, so if you're one of this, if you are one of the candidates who do something like that, can you please remember what I have said in this video? You simply can't do that. Okay, the current will change when your EMF is different. Yeah, so let me get this out. So what you should do is that you should find the R first, because the resistance will not change even though you change the input EMF. So what you can do is, of course, you use this formula, right? And then you go and sub all this thing in, and you'll be able to get a fraction like that. Then you can find the new power with your new V, and of course the same R, and you will find that your new power should be equal to about 37W. So with 37W, you should choose a diameter that is 0.75 mm. Yeah. So for those of you who are better in math, you will realize that there's another method lah. So I'm now sharing with you the shortcut method. If you look at this, if you know that your R, this guy, is a constant, that means this equation will look something like that. 1 over constant times V squared is the same, right? This thing is the same as KV squared. What? Because 1 divided by a constant will still give you a constant, right? So you can see that P is directly proportional to V squared. So there's a faster way of doing this. If you want to change the voltage by this fraction 5 over 9, you just need to change the power by square. Then you will be able to get the same answer. Okay, so this is a faster way. So in paper 1, when you are really racing against time, you can do this. But if you find that this is quite difficult to grasp, and your and your mathematics not very good, what I suggest you to do is do it step by step lah. Find the R first. So what you need to remember is, oh, my appliance's resistance is going to stay constant whether or not I use a 9 volt supply, or if I use a 5 volt supply, my resistance should be the same. Okay, so that's one way of doing it. Okay, what will happen when you have a thinner wire? So if you use a thinner wire, yes, the resistance will rise. But that is not what we are asking for. We want to know what will happen in real life, you know. So most of the time when you use a diameter that is shorter than the recommended diameter, it is in your textbook, you need to read about this in practical electricity chapter, okay, it will overheat. So if you use a thinner wire than the recommended diameter, basically your wire will overheat. This time round, we lower the marking standard. So some of you say the wire will melt. Actually, the wire is made of copper. Copper is metal. The melting point of metal is actually very high. What will melt is that the copper wire will overheat, and then the plastic webbing around it will melt. So in your wire, right, you have all these copper wires squeezed into this plastic webbing. So this wire will overheat, it will be turning very hot, but it won't melt. What it will melt is that it will melt this plastic layer. Okay, and when this plastic layer melt and continue to rise in temperature, it may ignite and it may catch fire. So for this particular case, this particular exam, we lower the marking standard and we accept the wire melt, but it's actually not true. We also accept that the wire will catch fire. We also accept electrical fire will be a result, but unfortunately there are a small part of you, a small number of you that actually says that the wire will explode chipapom. Okay, it's very seldom that we have practical appliances that will explode because it is hazardous. When the product is launched, the engineer will figure a way to make it not exploding. So if you watch Hollywood movie, right, when the car crash, it will chipapom, it will explode. But do you see explosion of cars on our highway? No, right? Imagine if every car accident result in an explosion, your highway cost will be so high, our taxes cannot cover the maintenance. So please do not use the word explosion lightly. Very, very, very unlikely you will have an explosion. Okay, Ken? Okay, let's continue with part B. So for part B, basically, when I set this question, I have turned the potential divider into a 3D diagram. So basically, it is a standard question. Here you can see that there's a thermistor, and if there's no information on the thermistor, you can assume that it is by default that when the temperature goes up, the resistance will drop, and vice versa. But if the question provides you with information on the thermistor, for example, in this case, there's a graph showing you how the resistance of the thermistor will change according to temperature, then you shouldn't rely on the default behavior. You should look at the graph and then make a decision. The other thing about this potential divider is that there is a variable resistor over here as well. And you were told that there is a 12-volt supply. So here in the next diagram, you will see a graph showing you the behavior of the thermistor. And I have been telling my class, but still very few of them are following. Whenever you get a graph that you need to interpret, the first thing you need to check is unit. So for example, here my habit of doing paper is that whenever I see that the unit is not a standard unit, so like this case, this is kilo ohm, meaning that there is a prefix over here, I will be extremely careful. Because whenever I use formula, I need to turn the parameter into SI unit, right? So my habit is that whenever I see a graph, the first thing I will look at is always the unit on the axis. And if I find that the unit is one with a prefix, I will put a star next to it to remind myself that I need to do some changes. Okay, so when you read the context, the other thing you need to pay attention to is this part over here, that the bell will only sound when there is a 9-volt supply. So in another word, they are trying to tell you that the potential difference here at the bell should be 9 volt. So in a certain sense, because the bell is connected in parallel with the variable resistor, that the PD over here is 9. And if you are having difficulty seeing a 3D presentation of a circuit, what I would suggest you to do is that just withdraw something like that, just turn it into a 2D one. Okay, so what I do is that I can see that the bell is connected to the variable resistor. So on the 2D version, I also put the bell over there. Okay, so let's now begin answering the question. So here it says that I have to determine the resistance of the rheostat, meaning that I want to find out this one. I want to know the R. So like I said in my previous video, whenever I do question, I try to consolidate all the information on the diagram itself so that I'm very clear what are the information I have used. And it says that the bell should ring. If the question says the bell should ring, that means my bell here should have a 9-volt supply, right? And this means that down here, my V is equals to 9 volt. So like I said, I like to consolidate all my information on one diagram. And then after that is here it says when the temperature reaches 90 degree. So here I want 90 degrees C. So 90 degrees C I need to refer to here. 90 degrees C is this line, and meaning that the resistance of my thermistor is 10, but like I said, put a star here, kilo ohm. So down here I would know that my resistance is 10 kilo ohm, meaning that 10,000 ohm. So I need to be very careful there. There are actually a number of approaches to answer this question. I will start with the most straightforward approach. So as you can see here, it is basically a series circuit because the bell has not been connected to the circuit yet. Yeah, so as a result, basically the EMF over here, the 12 volt, is going to be shared by the thermistor and the variable resistor. So as a result, I can actually write this statement that the voltage of the variable resistor, okay, maybe I use VR, variable resistor, is going to be share from the EMF, and it is going to be shared according to its resistance, right? So the combined resistance will be the resistance of the variable resistor plus the resistance of the thermistor. And of course, I want this ratio. So this is the most straightforward approach because you can begin to sub values into it. So the voltage of the variable resistor, this is the one that I want, right? 9 volt, so that the bell will ring. So I will put 9 over here. EMF will be 12. Then I do not know my variable resistance because that is the thing that I want to find. So I will just put RVR over here plus RT. RT from the graph we have found it to be 10,000. So here I will have 10,000, and if you solve this equation and make RVR, I mean the resistance of the variable resistor, the subject, you should be able to find that it is 30,000 ohm. So this is the first method. The second method, it is a bit more lengthy. Because it is a series circuit, basically this current here is going to be the same when it flows through the thermistor and the variable resistance. So we can find this first, yeah, because you know that it is going to be the same. So we can first apply V equals to IR to the thermistor. So you may be asking me, teacher, how do you know that you should apply to the thermistor first and not the variable resistor first? You can do the other way, but why I do that is because since I know the resistance of the thermistor, so now that I can sub in value, the PD across the thermistor, because my EMF is 12 volt and I have already used up 9 volt on the variable resistor, so meaning that down here the voltage will be just 12 minus 9, which is going to be 3 volt. So with that, you can put it into your formula and you would know that the current flowing through the entire circuit is this value. You notice that when I'm doing a intermediate answer, I just leave it in fraction, it's fine. Okay, then once you know the current, you can then apply V equals to IR to the variable resistor. So for the variable resistor, you want it to have 9 volt so that the bell will ring, right? And then the I is the same because it is a series connection, and then you can find the R from here. You will get the same answer. Okay, let's continue with part 2. So for part 2, many of the candidates find this question challenging because they couldn't figure out the exact relationship, and many of you rely on mental deduction, and then you get all the relationship mixed up because you have to think what, like temperature rise, resistance change, and then is it drop or rise, and then how will it affect the PD, is it up or down? So a lot of these things, if you keep it in your mind, you will get very confused. So what I suggest for you to do is to write it down. Here I will give you 2 approaches, okay, for different types of student. If you are the type of student that rely very heavily on equation, then the best way to analyze relationship is to look at equation. So I will share with you the first approach. So here, if you look at the question, right, they are asking you, they want a lower trigger temperature and they want to know how could you adjust the resistance of the rheostat so that you can trigger the alarm at a lower temperature. And you need a mathematical expression to relate all these things, right? And here you can see that you actually already got one. So if you look at this relationship, you see that there is the trigger voltage, which is 9 volt. You want it to trigger, right? And you want to have the setting of the rheostat, which is by its resistance. And then you also have the trigger temperature, as in the resistance of the thermistor when it is at the trigger temperature. So if you take this formula, you take this mathematical expression and you write it over here, V of the variable resistor equals to the EMF being shared between these two resistors. You can actually work out, you can actually make the resistance of the variable resistor as the subject so that you will know how these parameters relate to one another. And it is quite straightforward. So let's play around with this and I will show you how you can easily do that. I understand that you all don't like algebra. So what we can do is that we can substitute as many constant terms, constant value into our expression first. So we know that we want our alarm to sound. So your voltage of your VVR will be 9. Our EMF is the same. And basically the rest of it, you will need to go and figure out, right? So you have all these things, right? Because you want to establish a relationship between these yellow highlighted terms and these green highlighted terms. So let's start. Okay, so I have 12 like that. Okay, I will do as much as possible in I try as much as possible not to skip any steps. So okay, I promise you I won't skip steps, so I'll keep to that promise. Okay, and then after that you bring this term over to the other side, and this term remains, and you will have did I do something wrong? No. Okay, and you have this. Twelve minus 9 is 3. So you have something like that. But you want to make RVR the subject, so you get this. So what does this mean? This means that in order for the PD across the variable resistor to be 9 volt, your resistance of the variable resistor has to be 3 times the resistance of the thermistor. And in our case, if we want to lower the temperature, our resistance of the thermistor, according to the graph, if you have low temperature, you will have a high resistance. So this means that your resistance of the variable resistance must increase. So for this particular approach, what you are doing is that you find an expression that will relate your resistance of the thermistor with the resistance of the variable resistor, and then you simplify this expression and you find a relationship. Then it really depends on how skillful you are in your mathematics. You have to make sense of what does this expression is trying to tell you, and then you apply what you see in the graph that relates temperature and resistance, and then you can make a conclusion. So this approach is for students who are stronger in mathematics. So how about students who are not so strong about mathematics? And that is the majority, right? So if you are not so strong in mathematics, what you need to rely on is you need to have a way to organize your thoughts. If you can't do that, then you will also run into difficulties. Okay, so how to organize it? So let's make use of what we have done previously in part 1. So in part 1, we learned several things. We know that at 90 degrees C, your resistance of the thermistor is 10 kilo ohm. Okay, so let's use kilo ohm because if not, there will be too many zero. And in order for the bell to sound, you calculated and you found that your resistance of the variable resistance has to be 30 kilo ohm. And by having such ratio, you will be able to get 9 volt at the bell, and then you will get the remaining voltage at the thermistor. Right, that is fine. So you have organized your data and you get this. Okay, let's say you use the same resistance. Okay, but this time round, you are having a temperature of, let's say, a very low temperature, let's say 20, and at 20 degrees C, you are getting 55, right? You are getting 55. So 55. And just by looking at the ratio, you will know that this voltage over here will definitely be less than 9 volt, right? And basically your bell will be off. So what the question wants is that, let's say now I want the bell to ring at 20 degrees C because I want to have the trigger temperature lower. So meaning that instead of getting trigger at 90, I need it to trigger at 20. So far, once we have organized this, then it is quite clear now that in order for the bell to be on, what you need to do is you need to make sure that this value goes up such that the ratio between these two is 3:9, right? So in order to get 3:9, and this guy is getting a bigger value, it's like 10k, you increase it to 55k. So in order to maintain the same 1:3 ratio here, from 30k you also must increase to a certain value, right? But the question didn't ask you to calculate what the value is. You just need to know whether you should bring it up or bring it down. So by organizing your data, it helps you to organize your thought and see the trend. So that's what I mean by organizing your data, and that's your approach B, because you don't need to calculate the exact value. You just need to know whether to bring it up or to bring it down. So once you have all these mental steps down, the next thing you need to know is you need to organize your thought and then express it out in a scientific, accurate manner, right? So how do I say that? Okay, first I want to let the marker know that, hey, I know how to do it, right? But if my deduction is wrong, and if I do that in my first sentence, the marker may take a look at the wrong conclusion and then just give me a 0, and I don't get any mark. So what I want to do is I want to put my conclusion last, right? So I will put my conclusion last. I will say hence increase the resistance of the rheostat at the last sentence. Then I will spend these 3 lines to actually build up my argument, right? So I will say something like, at low temperature, or I should use the word lower. At lower temperature, the resistance of my thermistor is high. You notice I didn't use the word increase or decrease because I'm not talking about a change with time. I'm just simply talking about the amount of resistance. So when the temperature is low, my resistance of my thermistor is high. I'm not saying that temperature decreases, resistance of thermistor increases. So decrease, increase versus low and high, also there's a implication to it. So at low temperature, the resistance of thermistor is high. So how will it affect me, right? So therefore, I will need a higher resistance at the rheostat to keep the ratio between resistance to 1:3. Okay, and hence I need to increase the resistance of my thermostat. So this way I have shown to my marker that when the question asks me to lower the trigger temperature, I am able to interpret the graph over here, and I realize that at a lower trigger temperature, my resistance of the thermistor will be higher. Then next, I'm trying to tell the marker that I also understand how would that affect my circuit, that when the thermistor resistance is high, I would need to have a higher resistance for my rheostat so that the ratio between the resistance is 1:3. Now, is this the perfect answer? I would say that it is not as complete as what I want, because it will be better if I have enough space and time to actually state that this 1:3 is the 1 is representing the resistance for the thermistor, and the 3 is referring to the resistance of the rheostat. So if I have time, and after I check paper I realized that actually this sentence not very good, I would want to add on to make it clearer. Yeah. So, and I also noticed that by writing this, it has the same effect of saying this. Correct or not? So in this case, I think what I will do is that instead of writing this, I can make my last line clearer. Keep the ratio between, so here I would write it clearer, between the resistance of thermistor to and resistance of rheostat to 1:3. No, finish explaining. Quite clear, right? Okay, for part 3, whenever you see the question word is suggest, it means that it is an open-ended question. That means I will accept a range of answer as long as it is sensible. Okay, so down here what happened is that if this is a fire alarm and if there is a fire going on over here, some of you are telling me that the heat will take some time to reach the thermistor, and it is wrong, because hot air rises. So when the hot air rises, the hot air will transfer the heat to the thermistor rather quickly. So there's no issue. But the problem is, if there's a fire here, what if it damaged the circuit? And as this is a series connection, right? If it damaged the circuit, meaning that your circuit will be open. So actually the main concern with such system is that if the fire damage the wiring, your circuit will actually be open, and the fire alarm will never on. So in real life, when you see a fire alarm over here, or like a smoke detector, right, actually the power source, the bell and everything, right, is in one unit. So it is isolated from the rest of the wall. So even if the fire hits the wall and all that, there's no wiring that will damage it, unless you put the